Now let's define what a binomial distribution actually is and the conditions that we have to fulfill for a problem to be classified as a binomial distribution. So the two main conditions are first, events. So independent events implies that we have the same probability in between trials. If we focus on our coin flipping from before, they're independent events because if the first coin flip was a head, the next coin flip is not affected by that result. So that's what we mean by independent. And the reason why we need events to be independent or trials to be independent for a binomial distribution is because of the calculation that we used before. So if we go back to the previous example that we talked about where we flipped 4 coins and we wanted to see what was the probability of flipping one head out of those 4 coins, you saw that we used the same probability for all 4 different combinations that were possible. And we can only do that because the probabilities were independent, which implied that the order didn't matter for those probabilities. Each of the probabilities were the same for each combination. Hopefully that makes sense. Second condition is that we have 2 outcomes and we classify them as a success or a failure. And you might notice that sometimes binomial distributions might not necessarily or explicitly have a success or a failure, or one event and then like the complement of that event. So sometimes we group them into different categories. So for example, let's say if we did a binomial distribution where we're rolling a dice and we're kind of focusing on whether we roll a 1 or a 2. So that's one outcome. Maybe we classify that as a success, rolling a 1 or a 2, but obviously a failure is just any other number that's possible. So it's not necessarily have to be like a win or a loss or a head or a tail or something like that. It could be an event where we just group, it could be an outcome where we group multiple possible outcomes together and then group the other set as well. Maybe we'll go through another example after this that's like that, so we can see how that's illustrated. For this one, it's a bit more basic. We have an example where if we play an arcade game, the probability of winning is 2/3. So this is a really clear win-loss, success-failure situation. And 5 games are played. So here's the binomial distribution formula. It looks kind of messy, but I'm just going to break down what each of these variables actually mean. So we can see that we've got n here. N is the number of trials. Okay? So n is the number of trials that actually happen. So in this case, 5 games are played, so n is going to equal 5. Now, x is the specific number of successes. So we haven't been specified that in the question yet, but that's probably what they're going to say. Like, what's the probability of getting 2 successes out of 5 or 2 arcade game wins? So x is the number of successful trials. Successful trials. And then P is, I'm just going to say POS, which stands for probability of success. Now that's the probability of success of each individual trial, not the grouping, right? So in this case, each individual trial has a probability of 2/3 of winning, and that 2/3 of winning happens 5 times. So the probability of success of each individual trial is going to be 2/3. Now, let's say if the question asked us, what's the probability of winning, as I said before, 2 games out of 5, 2 arcade games out of 5. So what we say is x is equal to 2, and then we substitute it into the formula here. So I'm just going to write down everything we know. N is equal to 5, x in this specific example is equal to 2, and the probability of success of each individual trial is 2/3. Now what we do is we plug it into the formula. Now as I plug it into the formula, I'm going to try and describe what each of these components of the formula means, because this is a very unique formula that's actually not on the formula sheet for some reason. I'm going to have a sip of coffee because I'm losing my breath. Okay. It's really early in the morning here, okay? And it's very cold. 5C2. This might give you flashbacks from year 11 methods. What does the C mean? Let's just do it up here. NCX is equal to n factorial over x factorial n minus x factorial. Now, you might not remember what this formula actually represents. It's the number of combinations of ordering maybe we'll do the general form, ordering x things from a bunch of n things. So for example, if this was 5C2 like it is in our example, how many combinations of 2 can we get from a set of 5, is essentially what it's saying. So what this is doing in our formula, in this specific example, it's finding the amount of combinations that you can order 2 successes from 5 trials in total. That's the way I think about this. So we'll go ahead and calculate it later when we need to. We'll just go through the rest of the formula. P is 2/3 to the power of successes, which is 2. This is pretty self-explanatory. P to the power of x is accounting for the probability of the successful trials happening. And then the other one, again, is self-explanatory after this one. 1 minus 2/3 is just going to be 1/3 to the power of 5 minus 2, which is 3. So this is accounting for the probability of the failures occurring. So we multiply the probability of the successes, and obviously it's to the power of how many successes are happening, and then the failures to the power of how many fails are happening. And in the start of this formula, which is probably the most confusing part, is just accounting for the different amount of combinations that we can have of the success failure ratio. Sweet. So let's go ahead and simplify this. 5c2 is 5 factorial over 2 factorial multiplied by 3 factorial. 2/3 to the power of 2. Just thinking, because we've got the 3 in the numerator, this is like a common thing that will always happen when you have binomial distribution. Your denominators are usually pretty much always going to be the same. So I like to leave it in terms of its powers, at least on the denominator for now. So 2 squared is 4. And then if I combine that fraction, 1 cubed is obviously just 1, but then it's going to be 3 to the power of 5 at the bottom. So 3 squared multiplied by 3 cubed at the bottom. I'll just leave it like that for now, because I know these are always going to get messy when you have bigger powers. So the 5 factorial divided by the 3 factorial. 3 factorial cancels out with the 3, 2, 1 from the 5 factorial. So we're going to be left with 5 multiplied by 4. And then so we have 5 times 4 divided by 2. 20 divided by 2, which is 10. So 10 multiplied by 4 over 3 to the power of 5. Okay, so still is messy. 3 to the power of 4 is 81, and then multiply that by 3 is 243. So we have 40 over 243 as our final probability. So yeah, you can see the calculation when you simplify it kind of gets a bit messy. Just wanted to emphasize the different parts of the formula again, just to make sure that everyone knows. This here is talking about the number of combinations of successes from our possible trial number. This is focusing on the probability of all the successful outcomes happening in our combination, and this is focusing on the probability of the failures happening in our failure combination.